Okay, so today what we're gonna do is we're gonna try to define integration in multiple dimensions. Okay, integration in multiple dimensions. Dimensions, if I can spell dimensions. Okay, and the way we're gonna start is we're gonna ask ourselves like, why do we even care, right? Why define such an object? Um, Well, one very easy answer to this is because it generalizes the integral to many dimensions. Right? Uh, it generalizes integrals. Okay. But that's a that feels like an excuse, right? Um, a better explanation for this is let's say we wanted to figure out let's say there's some force, right? And I'm moving through this force field. And my question to you was, how much work did this force do on me? Right? If you wanted to ask, if you wanted to answer this simple question, how would you do it? And it turns out that you need to integrate a certain object over a certain path in higher dimensional space. Because in even in two dimensions, let's say I'm just on the road, for example, I have many different paths that I could take. Right? Between any 2 points, there's like an infinite number of paths I could take. Um, so the work definitely depends on the path that I take. Yeah. There will be some situations, as we'll see, where the integral does not depend, like the work does not depend on the path that we take. But we'll reserve this topic for some other day. So okay, work done by force. So that's another way. Another thing is, let's say we had some fluid. Okay. And the question is how much in a small portion, how much fluid is coming in and going out? I just want to know the net flux of the fluid. Um, and we'll see that this also requires you to do a certain integral. If you wanted to calculate the mass of an object in 3 dimensions and you're given the density, how would you do that? That's a three-dimensional integral. So we see that there are many reasons why we would even care about defining the integral in multiple dimensions, right? Okay, so let's start with this. Let's start with this work done by a force. Um, let's start with this work done by a force. So um, let let's say the force is given by some like vector function f. Okay, and it takes in a position and tells me how much force um, there is at that point. Um, and now say that I don't know, go like this, right? Like something like that. I start here at time t 0 and I end here at time t, I don't know, 1. And now my question is, when I'm at this point, right, at I don't know, t 1/4, how much work has this force done along the path? So the force could look something like this. Um, I don't know, something like that, and then 0 here. Right? How much work has this force done? To answer this question, let's do it the way Newton would have done it, right? And it's if I look very close and I move just a little bit along um, the curve, how much force is done there, right? So let's say I move just a little bit. What I mean by this is I go from, so let's say I call my curve gamma. Let's say I go from gamma of t to gamma of t plus dt, right? Or let's not call it dt, let's call it delta t, because that's what we called it like last on the weekend. Okay. And now we can use ideas from the derivative to see that this is approximately um, gamma of t plus gamma prime of t times the variation, right? This is sort of the definition of the derivative. And now the question is like, the question is, how much work has the force done when I move from gamma of t to gamma of t plus delta t? Um, and one way to see this is how much of one way to see this is my force, like how much of the force is with me versus how much of the force is against me. And the way we figured out how much, like the way we know this from like linear algebra is we have to take the dot product of the force with our position because that'll give us the projection of the force onto the position. And we'll see how much of the force is with me versus against me. And so to see this, we look at f at gamma of t dotted with this like small variation in length. I'll call this variation in length delta t. And we saw that sorry, I'll call this delta gamma because we're moving along gamma. So delta gamma at t. So so we see that this is delta gamma is going to be the derivative, right? Is going to be the derivative times this small step. So this is approximately um, f at gamma of t dotted with gamma prime of t um, delta t. Okay. So this is how much work is being done in a small portion. And now I can add up all these works, right? And when I add up all this work, I get an integral, right? Just from one-dimensional calculus. So the work done now is from time t equals zero, sorry, time t0 to t1 of this f of gamma of t um, dotted with gamma prime of t dt. Okay. Are there any questions for how I got here? Okay. And now I could, and now we see that this sort of depends on how we parametrized um, the curve, right? Like if I move like two times faster, right? That shouldn't really have an impact on like what the curve, like what the integral actually is, right? What the work done actually is. Um, and so we can rewrite this. We can rewrite this in this form. So it's the integral over a curve, right? So I'll explain the distinction between C and gamma in a bit. Um, F dot dl, okay? And I'll explain what these are. So now what's the difference between C and gamma? So gamma is the function that takes in a time t and gives you a position of like where you are on the curve, okay? And C is the curve itself. Or in other words, you can think of it as the image of the parameterization. Okay. So gamma is sometimes called the parameterization of C. Um, and C is the actual like curve in space. Gamma is I give it a time, it tells me where on the curve I am. So that's this small distinction. Um, and now we see that like DL is a small step along the curve. So we see that um, it's given by gamma prime, where gamma is your parameterization. Okay. Are there any questions so far? Okay. Now, the way we've defined the integral right now this one-dimensional integral in higher dimensional space, um, we see that um, the direction I'm traveling in matters. And it should, right? If I start here and I move this way, I should get the opposite work of if I start here and then move that way, right? So in this case, it does matter what the direction it is we're moving in. What we can define now is something called the line integral. The line integral um, of f along a curve um, c with respect to length. Okay. So all this means is that if I move a certain portion along the curve, my integrating variable is like how much work is being done in terms of how far along the curve I am. Okay. And all I'm gonna do here is I'm going to replace this with the distance. So you're left with something that looks like this. Okay. Yeah. Actually, sorry, this should be, sorry, I made a mistake. This should be f from Rn into R, and this should just be f, like small f. Okay. So when we're defining the integral of a scalar function, we put in this like absolute value. But when we're doing the integral of a vector function, we don't put this absolute value. Okay. Okay. Now let's do an example, right? Let's do an example to see if this even makes sense. So example. Say I wanted to compute the length of a circle of radius r, right? So in other words, I want to compute the circumference of a circle. Now, I mentioned that if I integrate a function along a curve with respect to arc length, it's how much does the function contribute as I move along the circle, and I'm adding up all these contributions. So the function that I want to integrate is the function f of x equals 1, right? Along a circle. And just for simplicity, what I'm gonna do is I'm gonna assume that this circle is centered at the origin. It doesn't really matter too much, but yeah. And I know a parameterization for a circle is simply the radius times of um, cosine of t times r sine t. You can check that this will put you on a circle all the way around. And now what I can do is the circumference is nothing but the integral. So the starting time, I start at time t equals 0. And now I ask myself how much time does it have to pass so that I come back to where I started? And the answer is I have to go 2 pi, right? Because if I go pi, I move to the opposite side of the circle because cosine is negative and sine is 0. So I have to move another pi so I get back to the origin. So 1 times the norm of gamma prime of t dt. But what is gamma prime? I simply take the derivative of the components. Right? So I get negative r sine t, r cosine t. Um, and then I see that the norm of this guy is simply just r. Okay? So I'm integrating from 0 to 2 pi the function r dt. But this integral is easy. This is just 2 pi r. So so we do recover the circumference of a circle if we think of integration like this. right? If we think of integration along a circle. Okay. But now, what happens if I change parameterizations, right? What if instead I move along the circle twice as fast? Um, the circumference of the circle doesn't care about how fast you moved around it, right? The circumference doesn't care. So we would hope that this integral gives you something independent of the choice of parameterization. So we can test this out, right? So for example, if we chose a new parameterization where it's 2 pi times t and r is again 2 pi t. Now this is still a parameterization of the circle, but now I have to restrict t from 0 to 1 because I just want to go around once. So we look at the circumference as the integral from 0 to 1 of 1 times gamma prime of t, and then I take the norm of gamma prime of t dt. But if I take the norm of gamma prime, let's see. So if I take gamma prime of t, I get a 2 pi r out front and then negative sine t cosine t. But the norm of this is simply 2 pi r. Okay. So we see that in the two examples I've given, the parameterization of the circle didn't matter. So the length was independent of parameterization. And we can sort of see this because if we have a reparameterization and we take the derivative, we get an extra factor of the speed of the parameterization, right? And this extra factor of the speed of the parameterization is then canceled out by a change of variables um, for the bounds of integration. Because if I move two times as fast, my interval of one time rotation has to be one half of what it was previously, right? So the speed of the parameterization sort of cancels out the change of variables. We'll see more generally how the change of variable formula is defined, and then we can make it a little more clear as to what's happening. But for now, parameter like if I take the integral with respect to arc length, or sorry, with respect to length of a function, it doesn't seem to depend on what the parameterization of the curve is. Okay. Are there any questions? Okay. So so now let's sort of see what this arc length actually like what this d um what this thing means, right? What the norm of gamma prime dt, what does that mean? So let's draw a um, thing again. And I said that we're integrating with respect to length, and length is clearly the integral of speed, right? Um, my length is is the area under the curve of the velocity graph, which is um, and now we can ask like what is the length of this curve, right? Again, if I have gamma. Now gamma of t, I've drawn it in two dimensions, but it doesn't have to be in two dimensions, right? It could be in like n dimensions. And so to say this, I mean, we use our usual where EI is the basis, um, where EI is the standard basis of Rn. Um, okay, and now we could ask like, what is the length of this curve? Um, Now, if this was a straight line, we know what the length of the curve is very nicely. But what if it's not a straight line? Then we have to compute the infinitesimal length, right? Like if I move a little bit, how much length have I added? And then I have to add up all these lengths. Does that make sense? So I sort of have to figure out how much do I like instead of figuring out what the length is everywhere, if I zoom really, really close in, I can see that very locally my curve is a straight line, right? And I know what the length of that straight line is. Okay. So I'll write this as ds squared. So I'm going to use Pythagoras. So I know from Pythagoras, I move I move a delta distance. So I move a delta gamma 1 and then you know, square it. And then using Pythagoras, I sort of get this weird looking formula, right? So the the change in length as I move just a little bit is given by the variations along each individual coordinate axis, right? Um, so so then I can and now I just have to integrate this, right? But I have to take the square root. So I get ds is the square root um, of this of these variations. And what I want to drive home is I'm being very informal with what I mean here. Okay. We will formalize all of this as time comes on, but for now I just want you to have like an intuitive picture of what it is I'm doing. Okay. When I say variation, I mean the technical term would be the Gateau variation. But it doesn't matter. It just means like if I move very little, like if I move infinitesimally, how much length have I added? Um, and since it's the variation, we know that the variation is approximated by the derivative. Okay. So what I can say is that this ds object, whatever this is, this infinitesimal arc length that I increase, is given by nothing but the derivative of, sorry, the square root, the square root of gamma 1 prime. Okay, this is going to be annoying to write. So it's gamma 1 prime squared added up all the way to gamma n prime squared. But what is this? What is this object? This is precisely the norm of gamma prime. Okay. Technically, I mean, if you want to write it out in another way, that there should be a dt term here, dt. Um, we'll make sense of what this dt means. But it's like if I move like a tiny variation of what's happening. So the length of the curve is simply given by the integral along c of ds. But this is nothing but if I parameterize with respect to gamma, it's my starting time to my initial time of gamma prime of t dt. And I hope this sort of enforces the idea that this integral that we saw here, right, is with respect to this arc length, right? Okay. Are there any questions? Okay. So this is sometimes called the integral with respect to arc length and whatnot, but what I'm more interested in is this line integral we defined. So this was the line integral of a vector field along C. I'm interested in this line integral. Okay. So let's look at this. So instead of looking at vector functions, I can sort of redefine this for scalar functions. Okay. So I integrate basically along each coordinate independently. So one way to think about this is that so if I have a function from Rn to R, okay, then it makes sense to ask what is the integral along C, okay, of this function with respect to the ith coordinate. Okay. What is this integral with respect to the ith coordinate? And all this is going to be is it's going to be the integral from the initial time to the final time um, of f of gamma of t times gamma I prime of t dt. Okay. And then you can see with if you have a u sub, the integral is independent of choice of gamma. So I can choose gamma to be anything else. That still parameterizes the same surface or same line, and we'll get the exact same integral. So one can check. So this is an exercise. Check this is independent of choice of parameterization. Okay. So this is what a line integral is with respect to some coordinate axis. Are there any questions here? Okay. One thing I want to notice now is that clearly if I change the direction I'm traveling, this integral will give me a minus sign, right? This integral will flip. However, the integral with respect to arc length doesn't change because I'm looking at the speed rather than the velocity. Okay. So that's one thing to notice. So one thing to note is this integral cares about the orientation, right? It depends on if I'm coming in from the left or if I'm going from the right, or if I'm coming up, then down, and like it depends on how I'm approaching, right? But the arc length integral didn't. Yep. So that's something interesting. We'll mostly focus our attention on integrals with respect to these coordinates. Um, because as we saw with the force example, this is the more natural object to deal with, right? Because the force object gave us an integral of with respect to the coordinates individually. But and then we added all of them up. So let's actually write this out now. So I know that f prime like this vector function f has coordinate functions fi ei, right? And gamma has coordinate functions gamma I ei. But now I'm taking the dot product of f with gamma. And I'm going to use the fact that the EIs are like an orthonormal basis. So what I get is f dot gamma, sorry, gamma prime. So I did gamma prime is gamma I prime EI is nothing but fi. Um, how do I want to write this? Gamma I prime, where I sum over I. Okay. Another way to see this, I can lower this f index down here, just how we did previously. So I just lower the index. Okay. Does this make sense? So we see that over lines, we're integrating things um that look like so over curves, we are integrating objects that look like f1 dx1 plus f2 dx2 plus fn dxn, right? So if we saw, that's how we defined this integral with respect to coordinates, right? We saw that the natural way to define an integral with respect to coordinates is to integrate an object that looks like f dxi. Okay. Now, where these objects are called differential forms. Okay. So one way to think about differential forms is like it's an infinitesimal change in the thing. Um, but this is not a useful way to look at it when you're talking about manifolds, right, in general. So in Euclidean space, you come along with the notion of a little change. You know what a little change means. On general curved spaces without additional information, you don't know what this object is, right? So you can't really talk about this too much. So when we talk about manifolds, we're going to see that these are the objects that we want to integrate. But if you remember from the linear algebra portion, I called the um, the dual vectors for the standard basis, I called them dxi, right? So in some sense, we can see that we've sort of put in the ideas that um, multilinear, like alternating multilinear tensors gave us the notion of um, area. And we can see that area in one dimension is nothing but length. And every one tensor is alternating. So we see that these differential forms are alternating tensors. Okay. So these differential forms are alternating tensors. We'll look at like higher order tensor, like higher order differential forms later. But this is something we should keep in mind. Okay. Now let's say we wanted to integrate along C of f, like we wanted fi this. We see that this is nothing but the integral from the initial time to the final time of fj. I'll call this time init, time final here, just so that we don't get confused with things. And then if I'm just writing down the definition, right? This is gamma I prime of t dt. Okay. Now, if you've done the one of the exercises on the first problem sheet, um, you will recognize this object. Okay. This is called the pullback. We'll see why it's called the pullback when we talk about differential forms in general. But for now, this is called the pullback. One way to see why it's called the pullback is this dxi differential form is on the curve C, right? But when we come into our, like when we, this is a one-dimensional integral we know how to do, right? This is just what we've learned in like university, like first year, right? You see that the differential form we're integrating here, it has this dt term, right? And all these differential forms come into this dt term. Okay. And we also see that we're no longer integrating on the curve, we're integrating in R, right? So this thing is integral over the curve. And this is an integral over R. So we're somehow pulling back an integral along a curve to an integral along R. Okay. Does the no, like name make sense a little bit now? Like why it's called the pullback. Because instead of integrating along the curve, we're pulling back the integral to an integral along R. Okay. So the way we'll write this for notation is we'll see that we'll put this small star. Here, gamma is the parameterization um, of fi dxi, and this is going to be fi of gamma of t d of gamma, and this is going to be d gamma. And then we can see that d gamma will d gamma I. We'll see that d gamma I is nothing but gamma I prime of t d t. Okay. So this object here is called taking the pullback. And because we're pulling back integrals along curves into integrals along R. Okay. So does this make sense? Do differential forms in R make sense? At least what I've said. So for now, a differential form is nothing but an object that looks like f1 dx1 plus f2 dx2 plus so on. Okay, that's all what a differential form is. We'll see later on that differential forms are alternating zero. Did I call them zero K tensors? Yeah, I call them K0 tensors. So there'll be alternating K0 tensors um, on the tangent space. Okay. Now that I've mentioned the tangent space, let's briefly talk about what the tangent space means. So if I look at a curve, right? If I look at a curve, and let's say I'm moving along the curve, my question is, what are the possible velocities that I can have if I'm constrained to move along this curve? So let's say I'm over here. The only possible velocities I can have must lie on this line, right? I can't have any velocity that's not on this yellow line. Because if I did, then I'd deviate from the curve, right? So we'll formalize this, but this is called the tangent space um, at let's call this point P at P. Okay. So it's the tangent space at P of C. So C is our curve, P is a point on the curve, and then the yellow line is the tangent space um, at that point. Does that make sense? So one way to think about the tangent spaces is just the set of all possible velocities that I can have um, when I'm on this curve, when I'm constrained to move on this curve. Does that make sense? Yeah. Okay. So we'll formalize what it means, what the tangent space means um, later. But the idea is that you attach an affine space, right? You attach a line to my curve, and I can attach this line at every possible point, and then the collection of all these lines will be called the tangent bundle. Okay, so the collection of all tangent spaces will be called the tangent bundle. And will make sense for what the word bundle means. Bundle means something very specific here, and we'll see what that means. Okay. So this is integration along curves. Okay. And we saw that the way we want to integrate along a curve is the most natural way is we parameterize the curve and then we integrate along R. Right. So if I wanted to integrate along a surface, um, I'd have to parameterize the surface and then integrate along R2. But I don't know how to integrate on R2, right? And this is how we'll come into the topic of integration theory.
Sorry, I gotta go.
Yeah,
I have a class now.
that's okay. I'll see you on Saturday. Then.
Yeah.
Hi, see you.
Yo. Yo.
Okay, so we talked about integration along curves, and we saw that the way we integrated along a curve was we first parameterized the curve, and then we used the appropriate formulas. But this poses an issue because if we want to integrate over a surface, for example, we'd have to parameterize the surface, and then we'd have to integrate a region in R2. And if we had a volume, we'd have to parameterize the volume and then integrate over a region in R3. The issue is, how do we integrate over R3? What does that mean? And the way we're going to approach this problem is actually um, through measure theory and integration theory. So we're not going to be talking about the Riemann integral. Um, and we'll discuss now as to why we won't look at the Riemann integral. Okay. So let's start with one of the biggest issues with the Riemann integral, and that is it's not um, taking the limit of integrals may not be the limit of the integral. Sorry, the integral of the limit. So say I have a sequence of functions and I take the pointwise limit. The pointwise limit may not be Riemann integrable. Um, However, the uniform limit is Riemann integrable. But taking uniform limits is is an extremely terse and very hard to fulfill condition in many applications, especially in things like Fourier series. So the Riemann integral just seems to be too rigid to really work with.
What do you mean by limit, like pointwise limit of functions? Like functions plural? Like,
Okay, so say we have a sequence of functions f1, uh, fn, right? These are now functions. And then we're going to define a function f of x to be the limit as n goes to infinity of f of nx. So you take the sequence of functions, then you evaluate the sequence of functions at a point, and then you take the limit of that sequence, and that's your function value. Um, yeah. So
and what about the uniform convergence of functions? What would that
okay. So
look like?
uniform convergence of functions just means that okay. So a sequence of real valued functions uniformly converges if the supremum um, of like fn with f, like the supremum of the distance,
Mm-hmm.
less than epsilon eventually.
Okay.
Um, so you can, and a way to look at this is you look at the space of functions, um, and you give it the supremum metric, and then you talk about convergence in the soup norm.
Are these like implicitly being evaluated at the same point?
So the way this is defined, is this evaluated at the same point? No, this is not evaluated at the same point. The way you want to think about uniform limits is say this is my limiting function. Okay. What I'm gonna do now is I'm gonna draw like a tube
Mm-hmm.
around this function, and this tube deviates from the actual function by epsilon.
Uh-huh.
And what the uniform limit says is that if a sequence of functions uniformly converges, the the set of the functions remain in this tube after some point.
Okay.
So all but finitely many um are inside this tube eventually.
Okay. Yeah.
So that's what
So
uniform
like,
means.
okay, but in the case of continuous functions, does all but finitely many mean that we have to like it's just the whole function anyway? Because
Well, you're looking at a sequence of functions, right? So you could remove the first n functions, and then everything else is within this epsilon.
right, yeah, you said everything but finitely. many points in the function, right?
No, finitely many functions
Oh, okay,
in
okay,
the
okay, never mind.
sequence.
Okay, that's fine.
Yeah, so that's what the supremum, that's what that's what uniform convergence means.
Okay.
Um, so as it turns out, uniform sequence, like uniform limits of integrable functions, is integrable. But being a uniform limit um, is extremely hard. Let's give an example of a very intuitive sequence of functions that converges to something obvious, um, but it doesn't uniformly converge. So let's say I look at functions of this form, right? So they have a big spike, and then they come down, and then there's zero everywhere else. Okay. Um, this is at 1 over n. So from 0, so f of x is equal to, so this point here is n. So it's, um, so now we have to find the slope of this line. So the slope of this line is n squared. So it's n squared x for x in 0 to 1 over n. Then it's negative n squared x, and this is 2 over n. And it's negative n squared. So, okay, the slope of this line is, um, the slope of this line is negative n squared. And then if you plug in 2 over n, you should get 0. So n squared times 2 over n plus b equals 0. So that tells you that b is 2n. So this is plus 2n for x from 1 over n to 2 over n. And then it's 0 else. Okay. Now, if you look at this sequence of functions, the spike gets sharper and sharper and sharper. So point-wise, this sequence converges to the zero function. Right? Point-wise, it converges to the zero function. However, it doesn't uniformly converge to the zero function because for large n, this spike is arbitrarily far away from the zero function. Okay. So it's not. I don't know if this limit is Riemann integrable, but we can check this. So the area of this triangle is 1/2 a base. So the base is 2 over 2 times n, and then the height is n. So okay, in this case the limit like the limiting sequence is fine. Um, but one thing you might have noticed, so this is the integral. So the integral from 0 to 1 of fn of x dx is equal to 1/2 times 2 over n times n, which is 1. And clearly the integral of the zero function is not 1, right? So the limit as n goes to infinity from 0 to 1 of f of n dx is not equal to the limit as n goes to infinity of f of n dx. Okay. So this is one of the issues, right? Like the pointwise limit exists, um, and it still gives us something that's wrong. Um, okay, that's one of the issues. And now let's look at a sequence of functions that converges pointwise. All the functions are integrable, but the limiting function will not be integrable. So example 2, let's say. So let's call this example 1. Yep. So let me just say that the pointwise limit of fn was 0. Okay. Now consider the sequence of functions, and now it's given by two indices, okay? It's given by j and k, okay? And this is going to be the function cosine of j factorial times pi times x to the power of 2 times k. Okay. This example is due to well, his name in English is Henri Lebesgue, but in French it would be Henri Lebesgue. Um, Now, this sequence is interesting because this is obviously integrable. We don't know what the integral is really, but it is integrable because it's, composition of integrable functions. But now, the interesting fact is if we take j to infinity and take the limit as k goes to infinity of this function, we end up with the characteristic function of the rationals. Okay. In other words, this is 1 if x is rational and 0 else. Okay. And we can check this. So if x is rational and x has the form, so if x is rational and x equals p over q, if you take j to be bigger than bigger than q, right? J factorial contains q in its product. That means this q in the denominator cancels out with something in the j factorial, and what you're left with is an integer multiple of pi. But cosine to an integer multiple of pi is either 1 or minus 1. And since we're taking to the power of 2 times k, this is always 1. So if x is rational, this converges obviously to 1. Okay? If x is not rational, what happens is j factorial times x is arbitrarily close to any rational number we want. Not any rational number, but it the main point is that the cosine of j factorial times pi times x is never 1 or minus 1. So this means it's a number that's just less than 1. But if you take a number that's just less than 1 and then you take powers of it that keep increasing and go to infinity, this goes to 0. Okay. So if it's an irrational number, it converges to 0. If it's a rational number, it converges to 1. But here's the interesting thing. This function is not Riemann integrable. Okay. X is not Riemann integrable. Now let's see why. So let's say I take a lower sum of this with some partition. Let's say to see this, let's compute the integral from 0 to 1, okay, of this characteristic function. So if we look at any partition, it doesn't matter what this partition is, and we look at the lower sum, we know that it's you're summing over I times this infimum of the function, infimum of the function on the ith partition, right? And then you're multiplying it by the length of the partition. But any partition contains an irrational number, right? Any partition contains an irrational number. That means the infimum is always 0, right? So this sum is 0. But now if we look at an upper sum, all I have to do is replace the infimum with the supremum. Any partition contains a rational number. So the supremum is always 1. So I'm adding up the length of all the partitions, but that length is 1. So the lower sum for any partition is 0, and the upper sum for any partition is 1. So it's not integrable. But you see that's very inconvenient. We took just cosines and their powers, which show up in Fourier analysis. We took a pointwise limit, and the resulting function is no longer integrable. This means that the integral we use is flawed. Okay. So now we have to figure out how can we integrate functions better. Okay. Are there any questions so far? Okay. So we saw where the
Actually, remind me what we need to have for the upper and lower sums for it to be integrable. Do they just have to be like sufficiently close?
yeah, so in the limit they have to be the same.
Yeah, okay.
So
It's
as I
been a
make the
while.
partitions finer,
Yeah,
the upper and lower sums have to be arbitrarily close.
right.
Okay.
Okay.
So let's take a step back and let's see the issues. So in example one, we saw a limit of functions where it like pointwise converges to an integrable function, but the limit of the integral is not the integral of the limit. We'll see that the integral that we form will also not be able to solve this issue. The reason it won't be able to solve this issue is because the function is not bounded. Okay. So sort of the sequence of functions goes off to infinity, right? So you get a spike at zero in the limit, essentially. So the function is sort of the integral over zero, and then at zero it's infinity, but it's also zero at the same time. So we're gonna like ignore functions like this to begin with. Okay. Okay, we're not gonna ignore these functions. We'll see under much less stringent conditions, we'll be able to swap limits and integrals. But this next example is much more troubling because all these functions remain bounded, right? All these functions remain bounded, and we still see that the limits doesn't like you can't interchange the limit with the integral. So so we're gonna develop something that will allow us in the case that the functions are bounded. It'll like allow us to answer these to like swap limits and integrals. Okay. So we're gonna do this in like a couple steps. So this is the first thing is we're gonna figure out like what is the Riemann integral doing, right? So the Riemann integral is sort of measuring it's measuring the function in a sense, right? Because you're taking the infimum of the function and the supremum of the function. And it's also asking like what is the length of a partition? Okay. So we're going to first answer the question on how do we measure how do we measure sets, right? What does it mean to give the notion of length to a set? Okay. So what does it mean to measure a set? Yeah. Um, let's be even more, let's be like specific in our question. In Rn, what does it mean to measure a set? Well, I know that the volume of a unit cube is one. We learned this in elementary school, right? We would love for the volume of a unit cube to be one. So that's one of the conditions we're going to put. So we're going to define some function. We're going to call this mu. And it takes in things in the power set of R, n, and it'll give you a number between 0 and infinity included. Because clearly the volume of Rn is infinite, right? So we want to allow infinite volumes. So, but we're gonna impose certain restrictions on mu, right? So we know that mu of the unit, like the unit cube, should be one, right? Another thing we know is if I move, so if my cube is here, it has volume one. If I shift it here, it still has volume one, right? So translating doesn't really change the doesn't change the volume. So the way I'm gonna write this is if I have some set A, I'll add a vector t, and this just equals mu of A. Okay. Here A is a subset of Rn, and A plus T just means A plus T, where A is an A. Okay. So I just shift everything by A. Another thing I would hope is true is if I break this up into a bunch of distinct pieces, right? When I join them back up, I should get the same volume, right? So if I take mu of the disjoint union, let's say countable disjoint union, it should just be the, and so the volume of the union is just the sum of the individual volumes. So now my question is, does such a function exist? What do you think? Do you think such a function exists? You're muted.
Yeah, I'm trying to think. Um,
Like intuitively, do you think such a function exists? Like, give me the intuitive answer that you have.
um, yes.
Okay. I mean, yeah, I mean, the intuitive answer is yes, such a function exists, right? We should be able to measure the volume of any function we like, sorry, any set we like. But as it turns out, unfortunately, the answer is no. No such function exists. Unfortunately, no such function exists. I'm gonna put a star, like I'm gonna put a star around this. Okay, I'm gonna put an asterisk around this. The reason it doesn't exist actually depends on the axiom of choice. So in models of set theory where you allow the axiom of choice, no such function can exist. Um, in models of set theory where you don't allow the axiom of choice, then yes, such functions do exist. Um, but we unfortunately will take the model of ZFC, namely Zermelo-Frankel with choice. Um, and so no such function exists. A counterexample is very unintuitive to come up with, but if you want, you can look up the Banach-Tarski paradox. So the Banach-Tarski paradox. Essentially, what the Banach-Tarski paradox says is that if I start with a ball, I can break the ball up into finitely many pieces, and then I can join back the pieces in such a way that I get two balls of the same volume as the original ball. So it violates this one. Okay. It violates the third property. In fact, it violated it so badly that it didn't even require us to go up to an a countable disjoint union. Right? It broke it in a finite disjoint union. And the other issue is that we allowed translational invariance. Okay. So now we have to reevaluate, right? So we could either get rid of translational invariance and the disjoint union property, or we could say that not every set can be measured in this way. The nicer approach is to restrict the class of sets. Okay? So this forces us to restrict the class. I'll call it the collection just because class means something else. Collection of sets we can measure. Okay, so let's think about all the sets we can measure, right? So if I should be able to measure the empty set, right? I should be able to measure the empty set, and I should be able to measure the entire set as well, right? So now I've moved outside of the specific case of Rn. Okay. So I should be able to measure the empty set and the entire set. So let's say the set is X. Also, if I know the volume of one set, right, say any set, and I know the volume of the entire set, the volume of if I remove the set that I have from the entire set, I should be able to tell what the volume of the remaining is, right? So say this is my X. Say I know the volume of this, okay? If I remove this circular region from X, I should be able to know what the volume of the remaining portion is, right? Because I just subtract from the total volume. So if I know the volume of E in X, then I know the volume of X remove E, right? And to incorporate the third condition, because the third condition is quite general, right? It doesn't restrict to a specific set. We also say that if I can measure um, a sequence, so if I know the volume of EI, then I know the volume of the union. Yeah. I might not be able to compute it directly, but I know it should exist. Okay. So putting all these things together, we define something called a sigma algebra. So let X be a set. Then sigma, a subset of the power set of X, is called a sigma algebra on X if one, the empty set and the entire set are in sigma. Two, E subset of X with E in sigma, then X remove E is in sigma. Finally, E1 to En subset of X with EI in sigma, then the union is in sigma. Okay. So it's almost like the conditions for topology. Um, the only thing is I've replaced the finite intersection with complements, and instead of arbitrary unions, I've restricted myself to countable unions. Okay. Now you can use De Morgan's laws to show that the intersection is in sigma. Okay. Because the complement of the union is the intersection of the complement. Um, so you can show that. Okay, so sigma is called a sigma algebra, and then everything in sigma is called a measurable set. E and sigma is called measurable. Okay. And we call X along with sigma a measure space. Okay. Okay, so we have a measure space, which is any set with a collection of subsets that satisfy these three properties. And now the question is, why is it called a measure space? Right? Why is it called a measure space? We'll see that in a second. But now let's see an intimate relationship between topology and measurable spaces or measure spaces. So, um, if you remember, when we talked about topology, we took a collection of sets that we would wish to be open, and then we found the smallest topology that contains all these sets, right? We can do the same thing with sigma algebras. We can take any collection of subsets and say, okay, we want these to be measurable. What is the smallest sigma algebra that contains these things? Okay. So I'll leave this as an exercise. It actually follows extremely quickly. Um, if so if sigma alpha are sigma algebras on X, then the intersection over alpha of the sigma algebra is also a sigma algebra. Okay. I think it's very easy to check because I think it follows almost directly. That this you don't have to do much. So what I'm gonna do is we're gonna take a collection, take any collection A of subsets of X. Okay. Then define the sigma algebra. Sorry, the sigma algebra generated by A to be sigma equals the intersection over so it's the intersection over, let's call it beta, which are subsets of the power set, and beta is a sigma algebra and A is a subset of beta. So beta contains A, beta is a sigma algebra. And then we intersect all of these. So this is just the sigma algebra. And then we know that this is a sigma algebra by the exercise. Um, and we know that this is the smallest sigma algebra that contains this collection. And the reason for that is because any collection that contains A must be a subset of this sigma algebra by definition. Okay. If I ever need to, I'll just put a subscript of A. Note sigma A is the smallest collection, sigma algebra containing A. If A was a sigma algebra, right, then the sigma algebra generated by A is A itself. And the reason for that is A contains itself. So anything that contains A must contain A. And so the intersection is trivial. Okay. So, let X, sorry, I'm not sure why I drew it like that. Let XT be a topological space. Okay. Now what we're going to do is we're going to say that the open sets in X are measurable. Okay. So we want to be able to measure the open sets in X. So the sigma algebra, sigma T, right, is called, so it's so important that it has its own name. It's called the Borel sigma algebra. Borel sigma. Okay. I'm not sure who Borel is, if I'm being honest. I don't know why his name is. I don't even know if it's a person. Um, but yeah, we call it a Borel sigma algebra. Um, yeah. Okay. Are there any questions regarding Borel sigma algebras? Okay. So now let's come back to Earth a little bit and um let's look at like let's look at an easy example. Like what is um can we sort of describe the Borel sigma algebra of Rn with the standard topology? Okay. The answer to this is I don't know. Um, I guess it depends on what you mean by describe. Borel was a French mathematician. Okay. Yeah, okay, so he probably did something with Lebesgue. Um, because I'm pretty sure Lebesgue was the first one who introduced the idea of measure theory. Because that's his PhD thesis was on
He worked on measure theory, Borel. Like he was doing measure theory and probability, apparently.
I see. Okay. Yeah, because I'm pretty sure Lebesgue was the first one who brought this idea up because Lebesgue's PhD thesis was on the Lebesgue integral. So he devised a new integral and then people probably like generalized his ideas. Yeah, so I don't know if you can describe the Borel sigma algebra of Rn. I guess it also depends on what do you mean by describing. Um, what I do know is that in R, you can restrict to a much smaller class of sets. Um, it turns out that the Borel sigma algebra is the same as the one generated by half open intervals. Um, this follows relatively quickly when you realize that every interval is the union of half open intervals. And then once you have that, you're basically done. Um, so I'm gonna say I don't know. What I do know is that even in R, things get very complicated in terms of figuring out what is Borel, say, like measurable. Um, and the reason for this is in topology, you have an easy condition of saying that uh, if I can find an open set within each point, then my set must be open. The issue is the same doesn't quite hold for Borel sets. Um, I will outline a I think okay. So let's show why things get sort of complicated. I'll show that any countable set is Borel measurable. Yeah. But to do this, what I'll do is I'll show that a point is Borel measurable. Not Borel measurable, sorry, is a Borel set. Yeah. So in R, we sh will show the set 0, just X is a Borel set. Yeah. Uh, Okay. But the way we do this is we just have to say that it's the intersection of some open intervals. And this is very easy. Just consider the intersection as n goes from 1 to infinity of x minus 1 over n, x plus 1 over n. In fact, you can actually do this interval. Okay, so once you know open sets are measurable, you know that closed sets are also Borel because closed sets are complements of open sets. Um, Now what I can do is I can use the nested interval theorem because I know that the diameter of this set is 2 over n. And as n goes to infinity, this diameter goes to zero, and all of these intervals are contained within each other. So I know that this intersection must be the set X. Okay, so points are Borel sets. This means that any countable collection of points is also a Borel set, right? In other words, this means that the rationals are a Borel set. In fact, what we've shown here is that um, we're one step closer to showing that the measure of a countable set is zero. So in some sense, the rational numbers in the real numbers have zero volume. Okay. So this is interesting, right? So things get very weird very quickly. Um, one can also show that the Cantor set is Borel set, for example. Okay. Um, so now I've talked about measures, like I accidentally keep calling things measurable. So let's define what a measure is. So a measure on so you need a measurable space, right? Is a function mu from the sigma algebra onto the set 0 to infinity, such that so one is I want that the volume of the empty set is 0, and two, if E1, En are in sigma and disjoint, right? Then the measure of their union is equal to the sum of their measures. Okay. So now you might tell me, okay, we haven't really fixed the issue because we've allowed a measure to have one of the main issues that we had. You would be almost correct. And when I say almost, I mean it's like there's a very small caveat. And one of the main things is we haven't imposed that this is translationally invariant. Because firstly, we don't even know what translational invariance means when we have an arbitrary set, right? Like if I give you some set, whatever it is, if I give you the set of all cats and I ask you, is this set translationally invariant? What does that even mean? Um, okay. And now the second question that someone might have is, how do you know such a function always exists? Because so far we've only talked about how such functions don't exist when you add one more condition. So how do you know such a function in fact exists? Um, and the answer to that is very simple. So firstly, I call this triple a measurable space. Sorry, I call this a measure space. Okay. Um, so what I want to note is that um, X sigma admits at least one measure. And the proof of this is as follows. Let X be a point in X. We know that such a point must exist if X is non-empty. Now, define, oh my God, define the measure of a set to be 1 if X is in E and 0 else. Okay. This is sometimes called the Dirac delta measure or the Dirac measure. And the reason this is called the Dirac measure is because if you know any distribution theory, um, this this looks like the Dirac delta function. When I integrate the Dirac delta function, I get 1 if 0 is in my set, and I get 0 if 0 is not in my set. So so working with the Dirac delta is in fact you just working with a measure. and you integrate with respect to a specific measure. So we see that the idea of measures have already been used, right? And we use them a lot in physics. It's just that we've never called it a measure. Okay. And we sort of hand waved it and said, oh, this makes sense because you have like this limit of Gaussian integral, like you have this limit of Gaussians, and then if I like multiply by my function, the integral sort of gets me whatever I want. Um, but I feel like that's a lot more complicated than it needs to be, right? Um, I feel like this is a much easier way of like doing things. But this is again just my opinion. Okay, so every measure space contains, sorry, every measurable space admits at least one measure. But this measure is not unique, of course. Right? Like I could have many different measures. Um, I could say, for example, that I mean, I think I can just pick any 2 points and say that okay, if one of the points is in here, I get one number. If I get another, if the other point is in here, I get another number. I think that works. Okay. So now this is the most general we're ever gonna get. Um, and we're not gonna talk about anything more general than this. Um, so let's get back to R. Let's get back to Rn. One more thing is if I have a measure space and the measure of x is one, right? If the measure of the entire set is one, this is called a probability space. And E in sigma are called events. So this is why measure theory is taught when you do probability theory. Um, okay, so let's just I'll talk about one final thing and then we'll end it for today. And that is how do we define the measure that we want in Rn? Okay, how do we define this measure? Okay, so what I'm gonna do is I'm gonna first impose the condition that so how to define a measure on Rn. So now one question you might have to ask is what sigma algebra are we working with? Right? The sigma algebra does play a big role. So what sigma algebra are we working with? So we know that the power set is a sigma algebra. Um, so let's just for now, let's just work with the power set and see if some things fail. So we're gonna define mu to be A1. So if I have the if I have a set of this form, okay, this is just a cube in space, and I know what the volume of a cube is. It's just the product of the lengths. So this is B1 minus A1 all the way up to Bn minus An. Okay. Very simple so far. I'll call these open boxes because they're open sets and they're boxes. And now I'm going to define mu of A. Actually, I'm going to call this mu star. You'll see in a second why. So this is the infimum over, so we're going to sum from k equals 0 to infinity of mu of ik, okay, where ik are open boxes and A is covered by the IKs. Okay. So the idea is simple. If I take a box, so if I take any set, okay, um, now what I do is I approximate the volume of this set with boxes. Okay. So if I have some set, say like this, one approximation I could have is this. Another approximation I could have is this, right? And I'm going to take the smallest such volume, okay? And I'm going to approximate it from outside coming in rather than inside coming out, okay? Okay. But now the question is this a measure? The answer is no. The answer is no. Uh, and again, the Banach-Tarski paradox is the reason for why the answer is no. So it seems like we're just back to where we started, right? Um, we went through this like whole shtick on uh, measures and like sigma algebras, and we came back and we answered no, this doesn't work. But not all hope is lost because what one can show, right, is that if I take a disjoint union, so if I take a disjoint union of things, what I do get is that it's sub-additive. Instead of being additive, it's sub-additive. Um, and what this means is that instead of us getting the same volume after we put the pieces back, we get something that's less than or equal to the individual volumes. And this fixes the Banach-Tarski paradox, right? Because we took apart a ball and we got two balls of the same volume as the original ball, but that's of course bigger than the original. So we're fine. So we call something like this a pre-measure. Okay. So if mu satisfies this, it is called a pre-measure. Okay. Pre-measure is such an unfortunate name. I've sorry. Um, okay. So I lost my train of thought. Okay, so we have a pre-measure. Um, I was gonna say something. I completely forgot. Okay, sure. Um, it turns out that if we restrict ourselves to the Borel sigma algebra, okay, if we restrict to the Borel sigma algebra um, of Rn, then mu star is a measure. So, woohoo, we found a collection of sets that is actually quite nice, right? We found the Borel sets um, of our form of measure. So we call this measure the Lebesgue measure. But now the of course there's another issue. It turns out that if you have a Borel set of measure zero, you may get that there are subsets of this measure, sorry, of this Borel set that are not Borel sets. Now, will you ever see such a set in practice in physics? No. You barely even see them in math. Um, but unfortunately, for completeness sake, we're just gonna add in all these like disgusting sets. Um, it turns out that in practice, it makes absolutely no difference whether we keep this set or not, like these sets or not, for physics, because they're like these are like set theoretical issues. Okay. So what we're gonna do is we're gonna extend. So we may have Borel sets of measure zero, whose subsets are not measurable. So we complete the Borel sigma algebra of Rn. So by complete, I just mean we add in all these subsets, and then we take the smallest sigma algebra containing everything. Okay, containing the Borel sets and all these like small subsets. Okay, Borel sigma algebra of Rn two. So what I mean here is add in all these subsets and find the sigma algebra generated by this new collection. By new collection, I mean Borel plus Borel subsets. Subsets of Borel, rather. Subsets of Borel measure zero. Okay. This new sigma algebra, this new sigma algebra is called the Lebesgue sigma algebra. And what we do is we just extend the like the Lebesgue measure to this measure, like to this thing. So we extend mu star to this. Okay, and this will be so we'll use the Borel sigma algebra and the Lebesgue sigma algebra pretty much like interchangeably. There's practically no difference. As we'll see, the key motto in Lebesgue integration theory is if something has measure zero, we don't care. Um, we don't care about that set. And if you have a subset of a measure zero set, it has to be measure zero. So we've quite literally added these Lebesgue sets that are not Borel just for the sake of completeness. Okay. I just want to end off with one last thing, and that is to show that every countable set um, has measure zero. Okay. Every countable set has measure zero. Okay. So, well, yeah. When I say this, I hope you know it's like with the Lebesgue measure, uh, you know, whatever on the Borel. You can either think of the Borel sigma algebra or the Lebesgue sigma algebra. It doesn't make a difference. Okay. So here's what I'm gonna do. So let A1, so I'm gonna this be an enumeration of A and R and so A is the countable set. Enumeration just means I list out all the elements one by one. I can do this because it's countable. Consider, so what I'm gonna do now is I'm gonna take boxes. Okay. Um, I'm just gonna take like you'll see. So consider I sub j to be the following box. So it's gonna be um aj okay, so it's gonna be j sub n. So it's like there's two indices. 1 over n and then sorry, 2 to the n minus 1. I should say n is different. Hold on. Let me call this m, and this is m. And I'm gonna do like that. Okay. Aj plus 1 over 2 to the m minus n, all to the n. Okay, so it's n copies of this. And now the Lebesgue measure of these objects by definition is just aj plus 1 over 2 to the m minus n minus aj minus 1 over 2 to the m minus 1, so minus n to the power n, right? This is just the definition of volume. And if we add this up, we get 1 over 2 to the m minus n to the power of n, right? But if I write this out, I just get 1 over 2 to the m, right? Because I have m minus, I should get m times n. I think I get something like this. Because I have 1 over 2 to the, so if I do in the m equals 2 case, I have m minus 2 times 1 over m minus 2, which gets me 1 over 2 to the, oh no, you don't. Sorry. Oops. This is wrong. Uh, yeah.
Don't we have 2 times?
Yeah, you're
No.
right there. You're right
Yeah.
there.
Okay.
I'm gonna get rid of this minus n and I'm gonna replace this with a 1. So I have ones here. So this gives me 1 over 2 to the m, all raised to the power n. Okay. Now, what I'm gonna do is that the union as j goes from 1 to infinity of these I, j, m's contains a. Why? Because it contains aj. And now note that um, the measure of A was defined to be the infimum of something. So what I'm going to do is now like these these I, J, M's, we know that it's going to be less than or equal to if I just summed each of them individually because they might not be disjoint. So it's going to be the sum as I goes from 1 to infinity of mu I, J, M. But what are these mu I, J, M's? Sorry, this should be a J over here, J, J, J. This is just 1 over 2 to the m to the power n. Um, this should be, sorry, I've made a mistake since the beginning. This should be a J here. I'm not sure where I got the m from. Sorry about that. J, 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 uh, J. Yeah. Now this is just a geometric series. Um, the way I can see this is if I just replace, this is 1 over 2 to the n to the power j. Um, Now the formula for the geometric series is it's the first term divided by 1 minus the common difference, the common ratio. So the first term here is 2 is this, and then the common ratio is 1 over 2 to the n. And if I write this out, I get 1 over 2 to the n times 2 to the n over 2 to the n minus 1, right? Which is just 1 over 2 to the n minus 1, which goes to 0 as n goes to infinity. Okay, so we see that the infimum is 0, right? Because measures are non-negative. They can be 0, but they can't be negative. So what this means is that the measure of A is equal to 0. right? This means that countable sets are measure zero. This actually gives you a proof that the real numbers have to be uncountable. And the reason for that is, oh, like, intervals have non-zero measure, right? Um, so if an interval contains more than one point, it must have non-zero measure. So that means it's uncountable. And now you have a set um, whose subset is uncountable, hence it must be at least uncountable. Okay, so we talked about measures and integration over lines. Next meeting, we will talk about how to integrate real valued functions on measure spaces. Um, are there any questions? Okay, if they're not, I will see you all on next time. Bye-bye.